Okay, so we're tackling the central question of whether a series converges, and we've previously looked at the divergence test, which doesn't tell us if a series converges, but can tell us if it will diverge. Okay, and we also looked at the integral test, and now we're moving on to the comparison test. There are two comparison tests that we'll consider. One is just the good old-fashioned comparison test, if you will, and the other one is the limit comparison test. So for the comparison test, we have this theorem. Let these two be, and again, the index, the sum isn't shown, the index from where to where, but these are infinite, okay? We could have wrote k equals 1 to infinity. Be series with positive terms, okay? We're looking at positive terms. If AK is less than BK, and BK converges, then AK must converge. And that is to say, if BK is this bounded infinite series and AK is less than this bounded infinite series that converges, then AK has to converge. What about if BK is less than AK and BK diverges? Okay, so BK is growing without bound and AK is greater than it, so it must also grow without bound. Okay, again, we're looking at positive terms here. So if we have this, then the infinite series with AK must diverge. So let's take a look at an example to determine whether the following series converge. So if we look at this, we could do the divergence test. We could take the limit as k goes to infinity. We'll get 0, and we get an inconclusive result. We'll also do the same thing here and get 0, and again, inconclusive result. So maybe we might want to do an integral test, but this looks kind of tricky with the integral test, and it's not too bad. You might have to do some u substitution there and play around with the integrand. Not too fun, okay? Doing the integral of this is, on the other hand, even trickier and not too much fun. And so let's use the comparison test instead. And now the central question that we have when we decide to do the comparison test is compare it with what? What series should we compare this with? And to answer that question, it's a good idea to look at the asymptotic behavior. Okay, so take the limit as k goes to infinity and look at what terms start to dominate. Okay, up here as k goes to infinity, k cubed is dominating. But down here as k goes to infinity, then the 2k to the fourth term dominates. This minus 1 becomes very small relative to the 2k to the fourth. And so if we look at that ratio, we'll get k cubed over 2k to the fourth, 1 over 2k. And so here's our candidate for what to compare this with after we did this asymptotic analysis. So let's take a look then at how 2k to the fourth, so we want to ultimately be able to compare with 1 over 2k. And notice that 2k to the power 4 minus 1 is strictly less than 2k to the fourth because you're subtracting 1. Now take the reciprocal, okay? Now we got ourselves the denominator here that we're after. Well, we need that numerator, and we could get it by multiplying by k cubed on both sides. Okay, so if we do that, now we do have our terms, and we have this over here, which reduces down to 1 over 2k. Now you could see why the asymptotic behavior was important. Okay, so we then have that 1 over, so we then have that k cubed over 2k to the fourth minus 1 is strictly greater than 1 over 2k. So looking at the comparison test, if 1 over 2k, the series with terms 1 over 2k diverges, well then so would k cubed 2k, so would this, right? Because of this test over here. And indeed, 1 over 2k diverges by the p-series test here. Okay, you can just factor out that 1/2. You have 1 over k, that's the harmonic series. And p there is less than or equal to 1. And so it diverges, and since 1 over 2k is, we just showed, strictly less than k cubed, it doesn't even have to be strictly less, it could be less than or equal to, then this will also diverge. Okay. What about b? Now you'll see a bunch of logs, and typically you want to use that log k is less than k. Okay, so this is advantageous when you're doing the comparison tests. For k strictly greater than 0, then log k will be less than or equal to k. Okay. All right. So we then could, we have that log k is less than k. We could multiply both sides by 1 over k cubed, and we have that that's equal to 1 over k squared. Now, if 1 over k squared converges, which it does, why? Because of the p-series test. P is equal to 2 here. That's strictly greater than 1. So you do get convergence. And so this term is less than the term for a convergent series. And so we have that natural log of k over k cubed will also converge. All right, well, let's move on to the other comparison test called the limit comparison test. And sometimes this is easier to deal with since you don't have to, sort of flip around the inequalities that might trip up some students. But the limit comparison tests could typically be used, whenever the comparison tests are used. And so and they're easier to work with because you don't have to deal so much with the inequalities. Sometimes, though, it's more obvious to use the good old-fashioned comparison test. Let's take a look at the theorem for the limit comparison test. So let AK and BK again be infinite series with positive terms again. So here we're dealing with positive terms. And let the limit as k goes to infinity of AK over BK be L. Okay. If that limit is strictly greater than 0 and strictly less than infinity, that is, L is a finite positive number, then AK and BK either both converge or both diverge. And that's sort of an awesome situation when you get a limit that's finite and not 0. Okay, finite positive number. Because, you could make a firm conclusion. On the other hand, if L is equal to 0 and BK converges, then you know that AK converges. Okay? If L is equal to 0 and BK diverges, you can't say anything about AK, on the other hand. Okay? So only if L equals 0, you do also need BK converging to reach that conclusion. If L is infinity and BK diverges, then AK also diverges. Again, if BK converges and L is infinity, you cannot say anything about A. So these two situations here are more limited when L is equal to 0 or infinity, rather than with one when you can make definite statements about the convergence and divergence of both series. So let's look at an example. Determine whether the following series converge. So, again, you take that limit. It's, the divergence test is inconclusive. Yeah, the limit there is 0, but inconclusive. And also the divergence test is inconclusive. You could also do the integral test, but that's a pain. I mean, you're already looking at that. You're going to maybe get some partial fraction involved there, and it's too complicated to do the integral test. So let's do the limit comparison test. Okay, we can do the good old-fashioned comparison test too, but it's sort of tricky with this sort of complicated polynomial. So what do we want to compare with? So we got our AKs. What do we want our BKs to be? Again, you take a look at the asymptotic behavior in order to predict what the BK should be. So as k goes to infinity, this k to the 4th term dominates, and this k to the 6th term dominates. Okay, so you'll get 5 over 2k squared. So we're going to choose bk equals 1 over k squared. We could have chosen 5 halves times 1 over k squared, but with limit comparison tests, that's not going to change very much. Okay, we'll then compare these two. We'll first take the limit of AK over BK. Here's our AK and here's our BK. And taking the reciprocal of 1 over k squared, so multiplying, we get this over here. And you could see, you could multiply top and bottom by 1 over k to the 6th, and then take that limit. But you could see that these are the terms that will dominate, and you get 5 halves, okay? You get 5 halves, and you could also see that it didn't matter, what sort of number we had in front of that 1 over k squared. At the end, we'll get a finite limit that's not 0 or infinity, okay? And now we are in that sort of really nice situation where it's strictly greater than 0 and not infinite. And so we could make a definite statement here. 1 over k squared, what we're comparing with, does converge, and hence this series converges, okay? And now let's take a look at B, which is a little bit trickier. So with B, some of you guys might be thinking, what if we do just a straight comparison test and take natural log of k less than k, but then you'll have k over k squared and you'll get a 1 over k there, okay? And 1 over k diverges. And so, these terms are less than 1 over k, and 1 over k diverges. We can't say anything but the comparison test with that, okay? Notice that natural log of k over k squared is somewhere in between 1 over k squared and 1 over k, which diverges. 1 over k squared is convergent, okay? And 1 over k is divergent. So it's a little tricky. And let's see what we could learn by a process of trial and error, okay? So we're going to take our AK to be the original series there. And we'll take our BK to be 1 over k squared. Let's just see what happens. So, here's our AK natural log of k over k squared, and B is 1 over k squared. Taking that limit, we get infinity, okay? So let's go up here and see what the L equals infinity tells us. If L is equal to infinity and BK diverges, then AK diverges. But BK does not diverge. 1 over k squared, okay? 1 over k squared is convergent. So we can't say anything. We're in case 3 here. We cannot say anything at all. It's inconclusive using the criterion of 3 there, because our limit was infinite. All right, well, we have, like we said, that natural log of k over k squared is somewhere between 1 over k and 1 over k squared. So let's try ck is over 1 over k is equal to 1 over k. So if we try to find the limit there, we'll then get, you have this indeterminate form of infinity over infinity. You could take L'Hopital's rule, get 1 over k over 1, and you'll get that's 0, okay? All right, so let's go up and take a look at our situation here. So the limit here would be 0. We called the limit m just because we wanted to separate it from the other L up there. So if we have that the limit is 0 and BK converges for us, we called that CK for that second part, then AK converges. But 1 over k does not converge, okay? It does not converge. So again, the limit comparison test is inconclusive. We can't say anything because our limit was 0, okay? And now you're getting a sort of idea of what I was saying about infinity and 0 are sort of the less optimal situations to be in. All right, well, let's do something super clever. And if k to the power 1 didn't work and k squared didn't work, well, why don't we just go right in the middle and do k to the 3 halves, okay? K to the 1.5. And now we take that limit, we're calling that dk now because we're running out of letters. And we're going to call the limit n. And so when we do take the limit there, we get natural log of k over root k. To evaluate that limit with the indeterminate form, we do L'Hopital's rule, get 1 over k, 1/2 k to the minus 1/2. We get 2 over root k, and we get 0, okay? Again, sort of not the optimal thing, but we actually do have, so we have limit 0, and p equals 3/2 does convert because it's strictly greater than 1. So you do have, that does convert. So we do fulfill the condition in number 2 here of the theorem, and so we can conclude the AK converges. Okay, this is 0. This does converge by the p-series test. This p is strictly greater than 1. Okay, and so we do get convergence there after some clever work.